Okay, so let's say we have a long solenoid and the radius of the solenoid is A, and it's driven by an alternating current, and so the magnetic field in the solenoid, which we know to be axial, behaves according to this expression, B naught cosine of omega naught t, where omega naught is some positive constant, and B naught is some positive constant. And let's say that it's in the k direction, so maybe the k direction is that one. Well, really what we want to say is that's the z direction. So we have the k hat unit vector, but that's the z direction. That tells us about the direction of the current around the solenoid. But we have a little disk of radius r. Let's say r is equal to a over 2, so we can fit that little disk into the solenoid and we rotate it. Actually, no. Sorry. Let's put the little disk into the solenoid such that we have. Well, let's make a drawing. So if we look at the solenoid from the top, like that, then we would see the solenoid of radius A, and let's say that we put our little loop such that it's facing us, so the normal to the disk is pointing straight at us. Okay? But the magnetic field is changing with time. And let's say that the little loop has resistance R, just resistance R. Let's find the induced current, right? What's I induced? All right, so we place the little loop inside. It looks like this from our perspective. From this perspective, we see the entire disk. Okay, so right, the induced EMF requires, so the induced current, if the loop obeys Ohm's law, is equal to the EMF divided by the resistance R, which is minus 1 over R times the time derivative of the magnetic field, of the magnetic flux, or minus 1 over R times d phi dt. And so the first thing that we need is phi. Right, what's the magnetic flux? Well, it depends on the orientation of the magnetic field and the orientation of the disk and the value of the magnetic field. So it's going to change with time. But we can see that at t equals 0, the cosine of 0, of course, is 1. And so we have a magnetic field that's just has a magnitude of B naught. So the flux will be B naught times the area of the loop, which is pi times r squared, or pi a squared over 4, because we squared the radius, and the radius is a over 2, times B naught. That's the flux at t equals 0, but of course the magnetic field changes in magnitude, and so we end up getting the cosine of omega naught times t here. And so the flux is changing with time, and therefore so is the so there is an EMF, and it turns out the EMF is also changing with time. All right, so we have to do this, and that brings in a minus sign, but the cosine, the derivative of the cosine in time is also a negative term, so we get a positive term. We have an omega naught coming out of here, so we have omega naught pi a squared over 4 B naught sine of omega naught t. So that's the EMF, and the induced current is therefore the EMF over the resistance, and that's just omega naught pi a squared b naught. This is also time dependent, omega naught t over 4r. And so let's get a sense of what's going on here. If we plot the magnetic field, right, here's the magnetic field, or the magnitude of the magnetic field. At t equals 0, the magnetic field is just b naught. And then the magnetic field varies sinusoidally. It reaches its lowest point and then comes back up like that. So this is sort of halfway through the cycle. And if we plot the induced current, then we get that as the magnetic field is decreasing, the current is flowing in one direction. So it's always has some value. So say it's positive. So it's like the sign. So this corresponds to this point. Now the magnetic field is going to start to increase and the current flips direction. So let's draw it like this as a function of time. Okay, so magnetic field decreases, current is in one direction, but also changing in time. And then when the magnetic field is increasing, the current flips in the other direction. And that's because the induced current, which produces an induced magnetic field, is trying to counter the change in magnetic flux.